Okay. Hi, everybody. So this work is about gesture recognition and more specifically about how to improve the recognition accuracy rates for gestures produced by people with low vision on touchscreens. And I'm going to start with an example. So here you can see multiple articulations of the same gesture type produced by 6 participants from the study. And in black, you see multiple articulations that were collected from a person without visual impairments. And in orange and dark red, you see these articulations of the same gesture type produced by 5 different participants with various low vision eye conditions. So visually, we can clearly see that there is more variation in how people with low vision produce this gesture type, but also others, with respect to the gestures that you see in black. Okay, so in order to understand why this variation in gesture articulation, I've searched the literature, and surprisingly, I found very little research that examined stroke gestures produced by people with low vision, and honestly, I did not find any explication of why this variance exists. And the large majority of work that has been done on accessible touch input had mostly addressed people who are blind. So from this perspective, people with low vision have been kind of neglected by the community. So in this work, I'm going to show that there are many differences in gesture articulation between the two groups, people with low vision and people without visual impairments. And I'm going to show that these differences impact the accuracy rates of popular gesture recognizers. And then I'm going to discuss what these differences are. And informed by these empirical investigations, I proposed 2 modifications for the P-dollar point cloud gesture recognizers in order to adapt it to address properly these variations in how people with low vision actually articulate touch gestures. Okay, so these are the contributions of this work. Okay, so I conducted an experiment with 20 participants, of which 10 participants with low vision, and the 2 groups were balanced with respect to age and gender. And each participant was asked to articulate several repetitions of several multi-stroke gestures. And in the end, a data set composed of 2,400 samples was assembled. Okay, so in order to evaluate recognition accuracy for gestures produced by people with low vision, I conducted a recognition experiment, and one of the variables was the recognizer. And I've employed 5 popular recognizers, which are all instances of the nearest neighbor classification approach, implementing various types of dissimilarity functions in order to compare candidate gestures with templates from the template set. So I've used the Euclidean distance, which is part of the $1 recognizer, the angular cosine distance employed by the protractor, and the point cloud distance of the P-dollar recognizers. And I've also included in the analysis the dynamic time warping dissimilarity function and the Hausdorff distance because of their popularity in other fields of studies. And I've computed user-independent recognition rates by controlling the number of templates per gesture type from 1 template to 64 different templates. Okay, so I'm going to summarize the main results. So one finding was that recognition accuracy rates improved for all classifiers and for both groups of participants with more templates per gesture type, which was an expected result. In terms of recognition accuracy rates, on average across all the experimental conditions and all the gesture recognizers, gestures produced by participants with low vision were recognized less accurately than the same gesture types produced by participants without visual impairments, and the actual difference was was of more 10%. And the point cloud recognizer was the most accurate of all the recognizers evaluated. And its best accuracy, its maximum accuracy, which was attained with 64 samples or 64 templates per gesture type, was of only 89.9% for gestures produced by people with low vision, while P-Dollar performed almost perfectly on the same gesture types produced by people without visual impairments, attaining 99.4%. So in order to understand these differences in gesture recognition accuracy between the two groups, I've conducted several gesture analysis procedures. One of them was to compute the consistency of gesture articulation. So gesture consistency is a measure that quantifies how consistent a user manages to produce the same gesture type over and over. And this measure and methodology comes from work done a few years ago, co-authored with Lisa Anthony and Jay Bobrock, and we also released a toolkit that automatically computes gesture consistency. It is called GECO, the Gesture Clustering Toolkit. So I've used this toolkit in order to understand differences in consistency between the two groups. And here are the results. So basically participants with low vision were significantly less consistent in their gesture articulations than participants without visual impairments. So, and the difference was statistically significant. So basically this means that people with low vision produce the same, produce gestures in many more different ways than participants without visual impairments. And in order to understand more, I've also looked at the accuracy of gesture articulations for the gestures produced by the two groups. And this time I've used another methodology and another set of measures, again work done a few years ago, co-authored with Lisa Anthony and Jake Wobrock. In this work we've proposed 12 distinct measures in order to evaluate how accurate users are able to articulate gestures in terms of the geometry of their shapes, and also how accurate users are in the time domain, and also their articulation accuracy can be evaluated. So we also have another toolkit for that. It is called GRADE Gesture Relative Accuracy Toolkit that I used in order to compute all these measures. Okay, so there is a lot of discussion about these measures in the paper. I'm just going to focus on two of these measures, which I find the most important for the modifications that I'm going to discuss a bit later. So one of them is shape error, which quantifies how much a candidate gesture differs in terms of the Euclidean distance from a template, from a training set, or from an ideal shape of that gesture type. So, results showed that participants with low vision varied their gesture geometry of their shapes significantly more than participants without visual impairments. So these results help to explain the differences in recognition rates that we observed earlier, and they also suggest that in order to address properly this type of variation that is observable in the gesture articulations of people with low vision, perhaps a different way to match candidate gestures to templates is in order. And I'm going to discuss about that in a few moments. And another important measure is bending error, which quantifies users' tendencies to bend the shape of their strokes with respect to, again, an ideal execution of a specific gesture or a template. Okay, so again, this time participants with low vision produced gestures that were significantly different than the same gesture types produced by participants without visual impairments in terms of the bending error measure. And The implication of this finding is that maybe local features computed on the gesture path, such as turning angles, which are used by the bending error measures, maybe these features could be used in order to perform better alignments between gesture points on the candidate and gesture points on the templates, in order to accommodate better this variation observed in gestures articulated by people with low vision. Okay, so now I'm going to present two modifications that I implemented in the algorithmic structure of the point cloud gesture recognizer. But first I'm going to briefly present its operation mode, in case you're not familiar with P-dollar. So P-dollar is an articulation-independent gesture recognizer. This means that it can classify accurately, it can recognize accurately gestures, no matter how users choose to produce them. For some multi-stroke gestures, there is a lot of different ways in which those gestures can be articulated. For instance, for a simple square, there are over 400 possible ways to produce it with 1, 2, 3, and 4 strokes. And the P-dollar recognizer uses a representation of point clouds in order to address this problem, because a point cloud is representative for all the possible ways to produce the square in this case. And the point cloud does not care about how users arrived at this end result. Okay, and then point clouds are matched using a one-to-one alignment procedure. So each point from the candidate gesture is aligned to one point from template gesture. Okay, so this is how an alignment looks like. So the first modification in the structure of the point cloud recognizer was to enable one-to-many point alignments. So this way, each point can be aligned, can be mapped to its closest point from the second cloud. In the figure, you can see the differences between the two types of point alignments. So in orange and dark red, you see the alignment being performed by the original version of the point cloud recognizer, and in green and dark green or black, you can see the same two gestures articulated, aligned by using one-to-many point alignments. So overall, there are not too many differences, except cases like this, where those 2 points should not have been aligned, and this happened because points that are aligned at the end of the alignment process, well, they settle for one of the points that are left unmatched in the second point cloud. And this does not happen when we can do one-to-many point alignments. And the second modification regards using information about the gesture shape, such as local turning angles that can be computed along the gesture path. And this idea came from examining the bending error measure, and actually it is the modification that amounted into the largest increase in accuracy rate, because it is actually the connections between individual points that form the shape of a gesture. For instance, if you look at the first at the point cloud shown in the figure, there are this point cloud is representative for multiple multi-stroke gestures. So in order to address this, I modify the Euclidean distance between points, and next to the standard definition of the Euclidean distance, I've also added the difference in turning angles, and these turning angles were normalized. So in the end, this is probably the most important figure from the paper. The modified version of the point cloud recognizer that was adapted to address the variations observed in the gesture articulations of people with low vision performed on average across all the training conditions. It delivered 94.7% accuracy, and for the first time in this paper, the difference in accuracy is positive. And the maximum accuracy reached by the modified point cloud recognizer was 98.2%, which is just an awesome value. And the bonus is that the modified version is also faster than the original point cloud matching procedure. This is because the time complexity of matching points in the one-to-many approach is has less time complexity than the original approach. Okay, so in conclusion, in this work I've shown that stroke gestures produced by people with low vision on touchscreen devices can be recognized as accurately as the same gesture types produced by people without visual impairments. I achieved this with minor changes in the algorithmic structure of the point cloud gesture recognizer, which was also the most accurate recognizer among all the 5 approaches evaluated in this work. And I also see this, this work as an example of how careful analysis of data collected from one specific population can inform better design, in this case of a gesture recognizer, to suit the variation in data produced by that particular population. And pseudocode and source code of this modified version of the point cloud recognizer will be available on the Dara family homepage. And also the gesture dataset that I collected in this work, composed of over 2,400 stroke gestures, is freely available to use for research, and as far as I know, this is the only public data set for gestures produced by people with visual impairments. Okay, so thank you very much, and I'll be happy to answer your questions.
Hi, Dr. Radu. I'm Ken Liu. I'm from Rutgers University. And I have seen you have used your p-dollar and modified it a little bit. Have you tested that your modified p-dollar on the normal gesture with the visual, with the normal visual gestures? I mean.
So the question is whether I evaluated the performance of the modified version of the point cloud recognizer on gestures performed by people without visual impairments. Okay, yes, I did, and the accuracy also improves by a few %. So this result kind of shows that there is more work to be done in this direction, and exploiting local features on the gesture path in order to align points, while the points of the candidate to the template can lead to even better accuracy for general gesture recognition.
So, in my understanding, could I understand that the modified p-dollar is the state-of-art gesture recognizer?
No. So the modified point cloud recognizer is an example of how recognition approach can be adapted to suit the articulation variance of a particular user population. In this case, it was people with low vision. So all the modifications were inspired by empirical observations resulted from gesture analysis of gestures coming from a particular population. So it is an adaptation of the point cloud recognizer for a particular user group.
Okay, sure. Thank you.